So plan for today is we're gonna finish up talking about elimination mechanisms. And most specifically, we already talked about E2 versus E1. We've drawn the mechanisms.
Yeah.
But predicting it turns out with elimination reactions, there's oftentimes more options for the types of products you can make. Because if you have your leaving group in the middle of a carbon chain, taking your protons from carbon 2 versus carbon 4 will give you two different products sometimes. So how do we decide which ones are most likely, or is it just a probability based thing is what we're going to spend some time on today. And then the second half of class and maybe the beginning of lab, we'll talk about NMR spectroscopy, which is basically, it's another way of shining light on something to see what the electrons are doing. But it's both more complex and has less ambiguity to it than IR spectroscopy. So it's going to be one of those things we use it in conjunction with IR spectroscopy in the formula, and it winds up being really helpful. So for starters, just a brief recap.
Yes.
If we're looking at elimination reactions, our two options are concerted, which is going to be second order, meaning did I ruin it already? So this first one is going to be E2. It's second order because it's concerted. And then the second step, or the second mechanism here, is stepwise. So our leaving group leaves, we make the carbocation, and then we have a base steal a proton and electrons move over to make a pi bond. So very similar to the SN2 versus SN1 in that it's either all happening in a concerted manner, in which case it's second order, meaning either your concentration of base or your concentration of your alkane, your haloalkane, can affect the rate. Or it's first order, in which case the rate is only affected by the concentration of your leaving group. And we already discussed this terminology a little bit. And I'm actually going to, so this is another one where different textbooks use the term a little bit inconsistently. So I'm going to try and be consistent, at least within our own. Where's my standard Greek? Oh, that's why. They moved things. There we go. So if you are ever wondering how to get different characters into Word or anything else, insert in symbols. The other thing you can do that's frankly sometimes faster these days, if you just go to you just Google whatever character. And then find the Wikipedia page that usually has it right there. If you know what it's called, you can do that. It's very, very old nerd culture, but you've seen the super complex emojis that are done entirely with characters instead of like emoji characters. That was basically people in the early 2000s scrolling through these character maps and finding different ways to make different faces and things like that. Like
that's really weird.
It's called a character map. It's everything that's in a font is in here. So it goes all the way, you've got all sorts of things, you've got mathematical symbols, you've got different languages, arrows, currency symbols, all that kind of stuff. So good life skill to know. If you want to find that stuff, if you don't know what it's called, if you know what it's called, Google it, find it that way, search it up. But if you want to, if you're not sure what you want to use or what type of arrow character or something like that, it can be pretty helpful, in particular with mathematical stuff. Like that. Anyway, back to the lessons I'm supposed to be teaching. So just a reminder, why it's really fighting me on drawing on the board today. The carbon that has the leaving group attached to it is called our active carbon. Where the discrepancy is some textbooks will call the active carbon the alpha carbon, but then they get inconsistent later on. So we're going to stick with the term active carbon is where the functional group is, and the alpha carbon is one carbon removed. There we go. They pushed some update. Now it's not touchscreen at all anymore.
You said we're going with active carbon as.
Active carbon is the one that has the leaving group attached to it, and then the alpha carbons are the ones surrounding, are one carbon removed from the active carbon. And so if our alpha carbons are different, that means there's more than one possible product we can get when we go through an elimination reaction. Right, because regardless of if it's E1 or E2, pulling hydrogens off of carbon 1 versus carbon 3 is going to give us these two different products. Now there's two that are equal here. So if it was just based purely on probability, we would expect to see the second isomer more. Right, because this isomer, there's a total of 6 hydrogens that we could grab, that our base could bump into and grab, that all give us this product. Right, all 3 of the hydrogens here, all 3 of the hydrogens here will give us the same product. They all give us this product, but in fact, when we measure it, we see that that's what we have less of. So clearly there's something else going on when it comes to the stability of the products, because there's only, and so 6-2, we would expect it to be something like a 3-to-1 ratio going the other direction if it was just based on the probability. So what does that tell us about alkenes in general? We must be seeing this product more because it's more stable, right? Or because there's something going on with the transition state that's causing this first isomer to be preferred. So with carbocations, how substituted something was affected how stable it was, right? In general, we're going to see the same thing with alkenes. Alkenes, because the transition state looks kind of like a carbocation, because when the leaving group leaves and we pull the hydrogen off, or it's going to, in general, we're going to form products that are more substituted. And that's what's called Zaitsev's rule. And Zaitsev was Russian, so there's a little bit of a discussion about how to anglicize his name. I think I've seen it spelled both of these ways. It's the same person though. It's just when you're coming from a Russian alphabet, we don't have all the same characters, so it doesn't get spelled the same way. So Zaitsev's rule just means that we're going to preferentially form the more substituted alkene. If we have a choice of what hydrogens to pull off in order to make an alkene, we're always going to form, not always, sorry. Zaitsev's rule says we're going to prefer the more substituted alkene.
For some little drawing thing.
Down here.
Or not.
So that doesn't work, but this one still does. I'm gonna try to switch to a different input and then switch back and see if, oh, now I've done it.